So we've been talking about temperatures and pressures and moisture now. Well, the interesting thing is, how do we move the air? Think about it. When we talked about temperatures, we talked about temperature advection, or cold air moving in or warm air moving up. When we talked about moisture, I showed you some images of atmospheric rivers. Well, how does that air move along that path? Why does it move along that path? So the question becomes, why does air move? Here are some examples of air moving. At the surface, we have a surface pressure map today. And you'll notice there's a nice low sitting right over Kansas this morning. Pressure gradient's not real strong, but is decent enough that we have 15 knots of northwest wind here, another here, some other winds blowing around the low. Notice they blow towards the center of the low as well. Then you go up here to the high. Winds are kind of blowing out from the center of the high, and they're very, very light, like 5 knots or less. Matter of fact, down over here, some areas that have no wind. Down in Florida, for example, as well, with the high. Down here, there's not much wind. So it seems like there's a relationship. Winds blow a little stronger where the isobars are a little closer together. Stronger winds would obviously be up in this area as well, up in Canada, northeast Canada here. And interestingly, at the surface, winds blow in towards low pressure some and out away from high pressure. So question still is, why? Why do the winds blow like that? Here is another area of winds aloft. This is at 500 millibar, halfway up. Notice the contours, similar to pressure lines. We've talked about that. And the winds are blowing all parallel, literally right parallel with the pressure lines. They do tend to make a circle up here where the low pressure is. Another area of low pressure down here, but they're not blowing in towards the low as much. They're blowing more, with the aligns the contours around the low. And notice how much stronger the winds are up here. We were looking at 15, maybe 20 mile an hour winds down there. Here, 70 mile an hour here. Some of the stronger winds up in this area, almost 100 mile an hour. And then we go up even higher in the atmosphere, 300 millibars, where the jet stream is. And we're getting winds. Here's 115 knots. It's 130 knots. 140 knots. Some pretty strong winds along here, right? So, again, blowing with right along the contours. So, all things I just wanted you to see here a little bit, get an idea of how the winds change with height, and let's figure out why all this is happening. So we're going to set with this a minute, and I'm going to set up a slideshow here. Then we're going to talk about these winds. So winds are a major influence of weather. So what forces push the air around? What is making those molecules move somewhere today? So all we're talking about wind is, we've talked about temperature and pressure and moisture. All are single elements. You give them an exact number, that's it. Well, wind is two components. There's the speed, which is an exact number. If I told you the wind was blowing 75 miles an hour, that's a number. But if I told you the wind was blowing out of the northeast or out of the southwest, or maybe it's out from the north, that's a direction. So wind has two components, a speed and direction. Think about it. When you're driving your car, when you're moving along, you have a speed. Your car is moving so fast, but your car might be making a turn around a corner or whatever like that. It's changing direction. So it is very much like the wind in that sense. It changes direction. So what makes this wind move? A force. If you go outside, your car is not working. It's stuck. for this day for whatever reason, but you want to move it off the road. How do you do that? Well, many times people just push it off to the side. Maybe a tow truck comes and pulls it off to the side. So there's a push or pull that is making your car move. The same exact thing is happening to the air. There's a push or a pull. So according to Newton, the man had the apple drop on his head, and he got all these interesting theories because of that. He says that force is equal to mass. Remember, mass is just all those little molecules in a little area times acceleration. So acceleration is just a change in speed. When you put your foot on the gas in a car, your car accelerates. Hit the brake, the car decelerates. That change in speed is an acceleration. It's all a force is, those two things combined. So that doesn't mean that the wind's moving at a constant velocity, because something had to accelerate it to get to that velocity. So there's a whole bunch of forces that act on the wind. One of them, pressure gradient. So if I have, like I had this past week, a large low that moved from the Midwest across the northern part of the United States, that low had a very strong pressure gradient with it. So the low had one pressure in the center of the low at times was down in the 970 millibar range. There was high pressures around it that were like 1020 or 1030. So over a distance, there was a pressure change of like 60 millibars. That pressure change is what caused the wind. Air is always, think about it, like a big bubble or hill. High pressure has a ton of air in it. The air is usually cold many times in the high, so it's dense, weighs more. So that weight of that air is going to push it to go to where the low pressure is. So that's all that's happening. When you see low pressure or you see high pressure, air is always going to try to move from that high pressure to the low pressure. And with that in mind, the steeper that gradient, the more the pressure changes over a shorter distance. It's like you roll a stone down a hill. If you're going off a cliff, that stone's going to just take right off and go. If it's a nice gradual slope, the stone's going to grow a little slower. Well, the same holds for the air molecules here. So the steeper that gradient is, the more pressure change, the faster the molecules are going to try to move towards the other. So that's the first force, pressure gradient. There's another one, centripetal force. When you drive a car, or if you're in a race, if you're a track person and you're running around the corner, do you feel the force? Why can you run around that corner and not just keep going straight? Because there's a centripetal force that's helping you make that turn. It's a force that's generated when we are turning. So it's going to apply when the air is turning, not when the air is moving straight. So here's an example of that centripetal force. It's like where the string holding this ball in place is working. The tension on that string, the pressure on that string to break. If that string breaks, that ball is going to go straight. But if it doesn't break, that ball is going to continue in a circle. That's centripetal force. All right, here's the most complex of all of them. You had the easy ones. Now we're going to get to the one that's weird. Coriolis effect. The Earth rotates. And because of that, if you think about it, if you were standing in Alaska, we'll say at 80 degrees north, which is pretty far up in Alaska, near the top of it. The circumference of the Earth up there is very small, right? So in 24 hours, you're going that circumference around the point. If I'm at the equator, the circumference is around 24,000 miles. Ballpark it. Look at the distance that person at the equator traveled compared to the person up north or down south. That generates a force on the air. That's called the Coriolis effect. So it deflects the wind. In the northern hemisphere, it deflects it to the right. In the southern hemisphere, it deflects it to the left. The Coriolis effect is strongest at the poles, and there actually is no deflection at the equator. So as you move north, there's more and more deflection. I had this explained to me when I was in college as if I was a very good pool player. Believe it or not, pool players actually take this calculation into effect, even though they don't realize it, by how they shoot the pool ball. The ball is going to tend to turn to the right just a touch in the northern hemisphere. So the very good pool player, if you put him at the equator and he becomes very good down there, if you move him up north, his game's going to be off because the ball's going to deflect more. Yes, he'll adjust, or she will adjust, but there will be a change. Friction is another force. When you're driving, if you had no friction, you can just keep right on going without much effort, right? When you're pushing your car off the side of the road, it takes a lot of effort. The reason that is friction. And there's friction in every level of the atmosphere. Down towards the ground, there's going to be more friction because you have hills, you have valleys, it's going to slow the winds a lot. The molecules are going to hit this and want to slow down. Up in upper atmosphere, you have turbulence. All fluids have turbulence. So that bounces you around when you're in a plane, for example. So all of these things work together to change the direction the molecules are moving and how fast they're moving. There's one more, gravity. The Earth has gravity, as we know, two objects being pulled together. On the Earth, gravity is always going to tend to work down. It does not impact horizontal winds. It only impacts the air motion in the vertical, first off. Secondly, because the Earth rotates, we have centripetal force holding you onto the Earth, not just gravity, but rotation as well. So there's actually two components for gravity on a rotating body, such as Earth. If you're on the moon, the same would hold. The moon rotates. So, not a lot. Anything that rotates, such as Mars or Venus or whatever, are going to have that. So, to summarize, we have each one of these forces acting on any air parcel at any given time. That's what makes the air parcel move. By knowing how important and how much each force is, we can determine the direction that air parcel is going to move. Where is that temperature going to go? That was over somewhere. Where's the moisture going to travel to? All of that. Or is the air going to be rising up or sinking down? All of that is determined by a combination of these forces. Now let's just start in the vertical. All right. We talked about pressure change. The greater the pressure change, the more that pressure gradient is, the more force it applies. Well, guess what? If you go up, the pressure changes pretty doggone fast. Think about it. 850 millibars, we'll say 100,000 millibars is the surface. It's 150 millibar pressure gradient in about 1,500 meters. So not even a mile. Nowhere on Earth do you have that kind of pressure change in the horizontal, only in the vertical. So there's an extreme push to have the air from the surface move upwards and out. Gravity is the only thing that's holding it here. So if gravity's holding that, it must be pretty powerful, right? Well, it is. And that's what's called hydrostatic equilibrium. If the forces are balanced, in other words, a little air parcel just sitting right there, not going either up or down, then gravity is balancing that pressure gradient force. And that is actually what happens most of the time. A parcel can still move up. If it hits a mountain, for example, it's going to go up. Or maybe it'll come down on the other side of the mountain. But it's going to move at a constant velocity if it stays in hydrostatic equilibrium. So that's the first theory. Now we talked about vertical motions. We like to simplify things in weather as much as we can. You just saw the list of forces. Well, let's see if we can get rid of a few of them. So geostrophic wind. Geostrophic wind has only two forces. We've taken out friction, or we've taken out centripetal force. All we're going to deal with here is Coriolis effect and pressure gradient. Now what you'll notice when I showed you the 500 millibar chart that the winds were blowing parallel to the isobars or contours, and they were doing the same up at 300 millibars. When you go up in the atmosphere, friction is less. So what do you get? You get Coriolis effect balancing the pressure gradient. Takes a little bit of time, but it works pretty quickly. You don't notice it really in the winds. So you have Coriolis effect and pressure gradient force balanced, and the winds will move right parallel to the isobar or contour. That's geostrophic wind. Two forces only. Gradient wind has a third. In other words, we see around, even in the upper atmosphere, around low pressure, around high pressure, winds blowing parallel to the contours, but they're moving in a circle. So we've had to add a third force because they're not going in a straight line. That third force pushes it inwards and around that circle, makes it do a contour. And that is the gradient. That is the centripetal force. So you have three forces: Coriolis effect, centripetal force, pressure gradient. That's a gradient wind. One more force. That's all that we added. So now we're going to go down towards the surface. We add friction. All right. So if you add friction, friction is going to slow the speed of the wind. Well, Coriolis effect is based on how fast the wind's moving. The stronger the wind, the greater the Coriolis effect, if we're staying at the same latitude. So in the upper atmosphere, we're saying pressure gradient force and Coriolis effect are balanced. There's no friction. However, down towards the ground, there is friction. We've reduced the wind speed, and what happens? They become unbalanced. That is why winds blow in towards in towards lows and away from high pressure, because of that unbalanced. Here you can see it. All right, we are a fluid, the atmosphere. So since we have a fluid, if you do something at the bottom of the fluid, it impacts the top of the fluid. So if I have divergence at the bottom, fluid above is going to want to come down to take its place. So the air will sink. If I have convergence at the ground, air is going to want to rise up. Can't go into the ground, so it's going to want to rise, and we're going to wind up with divergence probably aloft to help that. So these are all factors of why the air is moving, why that temperature moved from the Canadian rock out there in Canada down over your area, why it got so cold, why did the moisture come up from the Gulf or from the Atlantic Ocean or from the Pacific Ocean into your area, because of these forces. Why did the air rise to produce precipitation? Again, because of these forces. So if you understand how all these forces are working, and they're all related, remember, pressure gradient is going to be related to temperature and moisture. So everything is combined to make this happen. And here you can see again, winds moving up, whatever, where we have sea breezes. And think about it with the sea breeze. If I'm sitting at the edge of the water during the day, air is heated up over the land. Air is going to be forced to rise because it's getting warmer. Air from the water is staying cool, so it's going to come in and take its place, right? So I have convergence right there from one. But the water is relatively smooth, so there's not a lot of friction. So the air is moving along pretty quickly over the water. Now it's hitting land, and whoa, it's going to slow down because there's a lot more friction. That increases the convergence right along the coast, helping to cause the air to lift more. That's why we get the showers and thunderstorms along these fronts. The Great Lakes are a classic example of this. The mountains in West Virginia, pushing air into the mountains. What happens? It's got to slow down. It's got to go up the mountain. So it starts going up, slows down. Winds are still pushing in. Oh, it's going to rise even more. That causes the snow over the mountains in West Virginia. So you've now seen all of these factors that work together to cause your winds to move. I hope if you have any questions, let me know.